All right, so arc length, you're going to actually find in section 7.4. So 7.4 talks about arc length. And this is in terms of a function, okay? There's also arc length for a polar function. There's also arc length for a, what can I think of the other one? Parametric function. So there's three arc length formulas, but all you guys have to know for right now is the arc length for a function. So there are two formulas, but they're basically the same. It just depends on which way you're doing it. So I'm going to write the definition for you guys. It says, let the function given by y, so let the function given by y equal to f of x represent a smooth curve. Represent a smooth curve on the interval from a to b. Now, by the way, just so you know, to give you a little bit of context, this is supposed to be taught to you guys after you did rotations of solids in AB. So, you guys rotated using disks methods, washer methods. Did you guys learn the shell methods? No, you're not supposed to, but sometimes teachers will teach it. And then right after that, that's 7.3. 7.4 is next. Okay, so arc length. Now, you're not supposed to learn this in AB, but you are supposed to know it in BC. So that's where we're getting it from that chapter. Okay, so they're talking about smooth curves and things right there. So that's why they're mentioning it here. So given something like that, okay, from A to B, then the arc length of F, the arc length of F from A to B is, so they'll call it S equal to the integral from A to B square root of 1 plus f prime of x squared dx. Okay, so that's the arc length if you're integrating from left to right. Okay, from left to right. But you could also integrate from the bottom up, right? That's one thing you guys, if you remember when you did the revolutions of solids, right? You could sometimes do the revolution vertically, sometimes you can do it horizontally. It kind of one way was better than the other. So this is why they're going to mention two different ways. So they say similarly, for a smooth curve given by, so for a smooth curve given by x equal to f of y over the interval from C to D. I don't know if you guys remember, but every time you integrated vertically, you would use CD instead of AB, right? That's something they did in those lessons 7.1 and 7.2, where you were rotating. So anytime you see the interval CD, it's kind of a clue that this is going vertically. Okay, so if you're doing that from C to D, for us, the arc length is S equal to the integral from C to D of the square root of 1 plus f prime of y squared dy. So notice they're identical equations. They're not different. It's just the letters kind of change, right? Because the orientation in which you're finding the arc length is a little different. So this is the thing you have to memorize. So like I said, memorize this. Okay? Memorize this whole thing. Don't forget it. Write it in your cheat sheet for your final exam. Make sure you know it for your AP exam because it will show up. Okay, very important that you know that one. I mean, good that you know the second one too, but if you know the first one, the second one is just changing the a to b to cd and the f prime of x to f prime of y, dx to dy, but it's just the orientation that you're looking at. So here we go. Let me just give you the one example. I'll give you guys a little bit of time to work on it. Okay, but you're just going to basically punch this into your calculator and we'll be done. Okay, so example number 1. We're going to find the arc length of the graph. Find the arc length of the graph of y equals to x cubed over 6 plus 1 over 2x. And they say over the interval, so over the interval from half to 2. Okay, so just to give you a quick little sketch of what this kind of looks like, I'll just put it right here. Just a small sketch, nothing major. The graph kind of looks like this. Okay, and they're saying that they want it from like here to like there. That's what they want to figure out, the length of that highlighted area. Okay, like how long is that? Notice we can't just put a ruler up to it, right? So you have to find a way to measure curves. So this is how we do it using that formula. So first off, you are going to have to take a derivative. Okay, so if I may, I'm going to rewrite y 1/6 x cubed plus 1/2 x to the negative 1. Okay, and then I'm going to take a derivative of this. So dy dx is equal to 1/2 x squared, because the 3 goes down and becomes 3 over 6. So that's a half x squared plus, I'm sorry, not plus, minus, because the negative 1 is going to go forward, 1 over 2x squared. Okay, so all I'm going to do now is put this into my calculator, but let me write the equation first. S is equal to the integral from half to 2 of the square root of 1 plus, and then f prime of x is x squared over 2 minus 1 over 2x squared squared dx. And now is when you guys are going to use your calculator. Okay, so I'm going to pause this, give you guys a little bit of time to do that. All right, so again, your answer should have been 33 over 16, approximately 2.063. It does say 2.0625, but remember, 3 numbers after the decimal, right? So let's do example number 2 here, and then we'll move on to Newton's method, at least introduce it. So example number 2, we're going to find the arc length And by the way, the thing I'm about to do is trig. There's going to be a little bit of trig right here. So remember to be in radians if the measurements are in radians, like the angles. If not, you might get wrong answers. So find the arc length of y equal to ln of cosine of x from 0 to pi over 4. So again, that's a clue that you better be in radians. So first off, I'm going to get my derivative. So dy dx. Hopefully you guys remember how to take derivatives in natural logs. You guys remember? What do I do first? Well, 1 over cosine x. I always just do cosine x, because then whatever the, what goes on top? A what? Negative sine x, right? So that means it's a negative tangent of x. Okay, so there you go. So awesome, I have that. Now let's plug in the information. S is equal to 0 to pi over 4 of the square root of 1 plus negative tangent of x squared dx. So that's the integral from 0 to pi over 4 of the square root of 1 plus tangent squared x dx. What's the identity for 1 plus tangent squared x? Yeah, it's secant, right? It's just secant. Secant squared x. It's one of the Pythagorean identities. By the way, you'll notice a lot of these arc length problems tend to break down really nicely. So notice the square root of secant squared is just secant, right? So 0 to pi over 4 of secant of x dx. Now I chose this problem because there's a couple things you guys should remember. You should know all your trig identities still, hopefully. But you should also remember what the integral of secant of x is. It's not an identity, but it's something that you probably were supposed to memorize last year. Anybody remember what the integral of secant of x is? I'll give you a hint. It has a natural log in it. Yeah, kind of, but it's not secant of x tangent of x. Yeah, plus secant of x plus tangent of x from 0 to pi over 4. Okay, so at that point, plug in your information, use your calculator, and you should get approximately 0.881. Now, you could have skipped all these steps just by using your calculator, of course, right? But, just to show you what it looks like when you actually work it out by hand. Okay, but go ahead and try putting that in your calculator too. I'll kind of pause really quick. Let me just highlight the other answer. I'll pause really quick just to let you guys try it. Okay, make sure you guys plug that in. Make sure you're in radian mode, and we'll start off with Newton's method in a bit. All right, so hopefully you guys were able to get that with your calculators and got the right answer. Again, if you're having issues with it, just let me know. So we're going to move over to section 3.8. So section 3.8. This is Newton's method. Okay. So Newton's method was a technique to approximate the zeros of a function using tangent lines. Okay, so let me show you a picture of what was kind of happening. So let me see. I want this to be a lot bigger than that, so I may move the picture just a bit. All right. So here's the deal. This is kind of what he did. If we get let's say a graph that looked like this. And he was trying to figure out the zero. Now remember, he did not have a TI or a Casio, right? So he's trying to figure out where does this line cross the x-axis. Now he knew the function, and he knew that he could figure out like any type of derivative to it and stuff like that, right? So this is what he did. He said, okay, I want to try to find an answer to this problem between, let's say, A to B. Let's call this A. He wants to see if he can find an answer between A to B. So the first thing he did is he picked a point, okay? Any point. Let's say he picked X right about here. And he went up to the graph, put a point there. He called it X comma f of X, right? That's X comma Y. And he said, let me figure out the slope of a tangent line. Okay? So um, he basically said, okay, this right here, if I draw a tangent line to it, is here. Now, for him, it's easy, and even for you guys, it should be easy to figure out where a linear function meets the x-axis, right? That should be an easy thing to do, right? Y equals mx plus b, figure out when y is 0. That's an easy thing to solve. So he was able to figure out that 0. He said, oh, okay, here's my 0 right there. Okay, but is that the 0 to the function that he has? No, it's still off, right? So he said, well, how am I going to figure out if that point that I just found is the correct answer? Well, he did this. He got that point and he went to the graph. So let's call this x sub 1, okay? So that point right here would be x sub 1 comma f of x sub 1. And he said, let me draw another tangent line. And he found another point right there. Now, does that point look a lot better? Yeah. He doesn't know this, though. Okay, he has no idea. So he says, okay, I found another point. I wonder if that's my answer. So this is what he did. He says, let's call this x sub 2, okay? I'm going to take x sub 2 and subtract x sub 1. And if it's within a certain accuracy, then I'm going to accept it as true. But if it's really inaccurate, like if the number is like really big, like the difference is 5, then no. I want the number to be like 1,000th of a value off. Because then that means I'm getting close. And as I keep doing this, if the numbers keep getting closer and closer and closer together, eventually what's my error going to be? 0. That's the idea. So he says, okay, maybe this is it. So he goes up, he creates another little point on the graph. Okay, he calls that point f of x sub 2 and x sub 2, right? And he draws another tangent line. I know it starts to get really messy right here at this point, okay, and I do apologize, but I just want you guys to see it. Notice, let me zoom in real close. You see that tangent line, the purple line? It's like almost at the red. Okay? It's right there. And if he does it again, guess what the next point's going to be? It's going to be either the value or even closer. And all of his error calculations should be getting smaller and smaller and smaller, right? And if the error calculation actually equals to 0, what does that mean? You actually found it, right? You found your 0. Okay, so this is how he used to do it. Can you imagine doing this? Okay, thank goodness we have machines that do this for us now. Okay, but he would do this for any type of function because he didn't know what the functions like looked like exactly, like where they were going to cross exactly. And some of the functions are too hard to find out. You know, if you set y equal to 0, what's your x function, right? Or what's your x value? So he said, I got to figure out a way to do this. So he used tangent lines to approximate zeros, okay, over and over and over again, until eventually he was either pleased with the error, like maybe his difference was like 0.00001. He's like, well, that's close enough, we'll take that, right? One of the things you learn about mathematics is that they weren't always the most accurate numerically, but theoretically they were all correct. But numerically, you know, sometimes the calculations were a little off. Okay, but that's okay because now we have the machines that basically do it exactly the way they're supposed to be. So does everybody understand what Newton was trying to do with this? Is everybody, like, anybody a little still confused by it? So just use tangent lines to consistently get closer and closer to the zeros. Okay, now he did, there's this whole breakdown to it, but what we learned over the years with the APs, you guys don't have to know the breakdown, so we'll jump right into the definition, okay? So here we go, Newton's method. Now there are 3 steps in a sense. I guess it could be more, but 3 main steps. Let f of c equal to 0, where f is a differentiable function on an open interval containing c. Now what this means is make sure that there's a 0 that exists. Because if a 0 doesn't exist, then you're about to go on an endeavor that's never going to end. Okay, so make sure that a 0 exists. Now, how do you know if 0 exists? All the problems they're going to give you do have them. But again, we now have the technology to actually graph something and say, okay, there is a 0. You could actually find the answer so that when you're doing your work, it starts to make sense. Like, oh, my 0 was 2. I'm noticing I started at 4, then at 3, then at 2.7, then at 2.6, then at 2.5, 2.1, etc. Like you can see that you're moving closer to your answer. So that's why you might want to use your calculator to help you at least find the solution first, so that you're not like saying, oh, my answer is 3, but for some reason I'm lingering around 9, 10, 11, 12. Like something's off. Okay, so let's f of c equal to 0, where f is a differentiable function on an open interval containing c. So again, we're going to find an interval that the center is found there. Then, to approximate c, use the following steps. So step number 1, we're going to make an initial estimate. So in other words, guess. Go ahead.
What is like the point you're trying to find is like undefined?
Well, if it's a 0, it has to be defined. Yeah, it has to, that's what they say in the very beginning. Make sure that there's a 0. So don't go crazy trying to find a 0 for something that has no 0, because or else you're never going to find it. So yeah, make an initial estimate x sub 1. In other words, you're going to guess where your answer is, okay? So for x sub 1, let's put this right here. X sub 1 should be close to c. So again, I want you guys to graph these functions and find out where the 0 is. Because if the 0 is at 5, your initial guess, you might want to start at 4. Okay? That way you can do a couple of iterations. Iterations are a couple of steps. So you don't want to say, okay, my answer is at 5, so I'm going to start at negative 16. Because now you're starting so far away, you're going to have to do like 26 repetitions in order to even get close. So get close to it. If the answer is 5, heck, try 4.5. Get real close. Okay? All they want you to know how to do is the process for the test. Okay? So that's why you don't want to guess too good. Like if it's 5, you don't want to pick 4.999999. Because then you do it once and you're done. You don't really practice it. But get close to it. Okay? So get close to it. 2. Determine the new approximation and they give us a formula for this. So x sub n plus 1 is x sub n minus f of x sub n over f prime of x sub n. So that's how you find your new intersection, your new 0, okay? So you're going to find your new x value, your new x-intercept by doing that, okay? Now, to check to see if you're correct, you're going to check your accuracy. So if the absolute value of x sub n plus 1 minus x sub n is within the desired accuracy, so if it's within the desired accuracy, then x sub n plus 1 is your 0. Okay? If not, repeat step 2. So does it look like it's going to be a hard process to do this? I mean, you're going to guess a place to start. You're going to calculate step 2, and then you're going to just subtract your initial guess with your new number. And if it's within a specific accuracy that we deem is good, which usually the problems tell you like it must be within 0.01 accuracy or something like that, then you're done. And if not, do it again. Okay, find x sub 3, find x sub 4, find x sub 5, however many. Sometimes they're not going to care about an accuracy. They might just say, do 3 iterations. So you're going to guess, that's x sub 1. That's not an iteration, okay? When you guess, that's not called one attempt. That's called a guess, right? So your first iteration would be x sub 2. If they say they want 4 iterations, you have to go up to x sub 5, okay? Because you got to do it 4 times. You got to do the process 4 different times. So you'll start with x1, then you'll do x sub 2, x sub 3, x sub 4, x sub 5. Those are 4 calculations. Those are 4 iterations, okay? So let me show you an example of this. So again, I know I've been saying the word, but an iteration, okay? So whenever I say an iteration, this is each time you apply Newton's method. Now, the word iteration is not stuck to Newton's method. I mean, it's stuck to anything, but every time you do something, right? So even every time you play Call of Duty on your phone and you get killed and then you start again, you're now playing another iteration, right? You're just doing it again, right? So it's just another step. So that's what an iteration is if you've never heard of that in math. So here we go. Example number 1. And before I do this, let me check time. Let's try it. If we don't finish, we don't finish. We're going to calculate 3 iterations. We're going to do this 3 times. Calculate 3 iterations of Newton's method. Notice we're not really worried about the accuracy of it, but we'll kind of check to see what they are maybe later on. But calculate 3 iterations of Newton's method to approximate the 0 of, we'll start with an easy problem, f of x equal to x squared minus 2. And they're going to say use x sub 1 equal to 1 as the initial guess. Okay, so notice they're giving us the guess, they're giving us the function, and they're telling us how many times to do it. Okay, so if you remember the formula, it says x sub n plus 1 equals x sub n minus f of x sub n over f prime of x sub n. So that means I got to take a derivative. So here's my f of x function. That's x squared minus 2. And here's f prime of x. Because you need both. Okay? So there we go. We found both of them. Now, I know x sub 1 is 1. Again, this is not an iteration. This is a guess, so we don't start here. My first iteration is x sub 2. Now, x sub 2 will be equal to x sub 1 minus f of x sub 1 over f prime of x sub 1. Are we okay with that? Just plugging it in, right? It's x sub n plus 1 equals f of x sub n, right? So we're just kind of using that. You guys did a lot of that stuff when you did like sequences in series in algebra 2, so or the movement stuff. So all right, x sub 1 is 1 minus, what's f of x sub 1? Well, that's f of 1, right? What would f of 1 be? Negative 1, all right. What's f prime of x sub 1? Say louder. 2. All right, so what's my answer for x sub 2? I mean, 3/2, right? Or 1.5. Okay, there you go. One iteration. So I'm going to say first iteration, okay? X sub 3. Well, x sub 3 would be x sub 2 minus f of x sub 2 over f prime of x sub 2. Okay? We know what x sub 2 is. That's 1.5. F of x sub 2, in other words, f of 1.5, comes out to 0.25. Okay? So when you plug in your 1.5 into x squared minus 2, you get 0.125. And then f prime of 1.5 is going to be 3. Because it's 1.5 times 2, right? So it's 3. So now when we subtract that, 1.5 minus 0.25 over 3, you get 1.41667. I'm not going to truncate it right now, okay? So notice, at first we said the 0 was at 1. And then we said, nope, it's at 1.5. And then we said, no, actually, it's closer to 1.41667. Like we're slowly trying to get closer to our 0. Okay, so this is our second iteration. Let's do our third iteration. X sub 4. That would be x sub 3 minus f of x sub 3 over f prime of x sub 3. So this is our fourth, okay? Or sorry, third. And they wanted 3, so third iteration is right there. So first, second, third. So x sub 3 was 1.41667 minus f of 1.41667. I'll give you the answer for that. That's a 0.066954. I just wrote all the digits. Okay, and then f prime of 1.41667. Again, you're plugging that into 2x, right? So 2 times that. That would be 2.83334. So when we subtract it, we get 1.41422. Okay? Now, here's our answer. Let me just put right here, just to truncate it, we're going to put approximately 1.417. For this one, we'll say approximately 1.414. Now, just out of curiosity, what are the actual zeros? So we're actually done with Newton's method, okay? We're done with it right now. But what are the zeros for that function, f of x equals to x squared minus 2? Let's see. Let's figure this out. So f of x equals x squared minus 2. If I try to figure out the zeros, it's x squared equals to 2, which means x is plus or minus radical 2. What's the square root of 2? So, someone tell me, give me the first 3 digits, or first 4. 1.414. What are the rest? Give me some more digits. 1.414. 21. Look at that. I was at 1.41422. I started off at 1. Then I went to 1.5. Then I went to 1.417. And then 1.41422, right? Or 1.414. I'm getting closer. If I do another one, I may actually find it. Okay? Now, is my accuracy a 0 if I subtract x sub 4 minus x sub 3? No, I'm going to be off by 0.003, by 3 thousandths. But that's pretty darn good, right? That's pretty good. So, do you guys see how his method still can find things without, kind of, this is an easy function where he probably would have done it the way we did it, okay? But when the functions get more and more complicated, this can help you find it, this method, without a calculator, of course, okay?